In this video, we're going to talk about ideal and real gases. You should already be able to identify gases and explain their properties based on intermolecular forces of attraction, calculate the pressure, volume, and temperature of a gas using combined gas law, and memorize and utilize STP values. But by the end of the video, we'll review that stuff, and as well as explain properties of the ideal gas, converting pressure units, and then calculating those pressure, volumes, and temperatures, or moles, using the ideal gas law. So the questions of the video, and there's a couple, is how do we breathe? What's really going on? How do hot air balloons work, and how do they float? And why do water bottles left in cards implode after a while? So first, let's talk about the kinetic molecular theory of ideal gases. And so the gases, as you can see in the little simulation on the right, have no attractive or repulsive forces, so they're not drawing towards or away from each other like magnets. They have a negligible volume compared to the distance between them. So this is not a great model because the particles should be so much smaller than they're shown here. So the space is much wider. And the molecules are in constant, rapid, random, straight line motion. So if you look at the molecules and you take one to check on it for a while, they're going in straight lines. They're not curving. And they should constantly be moving. So the fact that it's restarting the simulation is the only reason why they're stopping. And the kinetic energy is proportional to the temperature, so meaning that any two gases with the same temperature should have the same kinetic energy. So we can measure that using this formula. The average kinetic energy is equal to 1/2 of the mass times the velocity squared, and then on average. Because if you see in the picture, at 150 Kelvin, they're not all necessarily going the same speed. Some of these darker particles are going a little slower. Some of them are going a little faster. You can tell by the size of the arrow. Similarly, around here, you have larger arrows, meaning they're moving a little bit faster. And they had different masses. So an average mass and average volume would give you this 150 Kelvin. Over here, again, some particles are going very, very far. Some particles are only going, very, very short distances, and they're different masses, or different sizes in this case. So again, it's the average of those masses and velocities squared that would give you this higher kinetic energy. So the more they move, the higher the kinetic energy is, and the higher the temperature should be. So when do the real gases that we have on Earth behave like these perfect gases? And that's at low temp pressures and high temperatures. So if you look at the ideal gas, where there's no forces of attraction between them, they would be able to bounce off containers and just completely go in a straight direction, but otherwise not attracted to each other. But real gases, we know, do bounce off the containers, but they also have attractions up to other atoms. So their speed might be a little bit slowed and things like that in real life. And that's because they, in an ideal gas situation, they should be spread out so much that they have no forces, right? And make those forces negligible. And make their volumes negligible, because the bigger they are, the more electrons they have, the more attractive force they should have. So to keep the more ideal, we should have them low masses, so they have less electrons and they have less attraction. So we should talk about these pressure situations where you push the gases together. If you push the gases together, they might form attractions. And so we should talk about the pressures in terms of the units you'll see. So the units we're used to are kilopascals and atmospheres, but we're also going to be talking about torr, millimeters, and mercury. These three numbers you should write down and keep the list of them and memorize them for the tests and quizzes. So we could set up a dimensional analysis and use these as our conversion factors for any of them, but my trick is just to divide by the unit I have. So if I have kilopascals, I divide by 101.3, or if I have millimeters of mercury, I divide by 760. And if I want a different unit, I multiply by the number I want. So if I want kilopascals, I multiply by 101.3. And if I want millimeters of mercury, I multiply by 760, because that's generally what you're doing in dimensional analysis. So if I was given 850 millimeters of mercury, I would divide by 760, and atmospheres is just a 1. So I would get 1.10. I would take time right now to pause the video and see if you can get the others before I go over them. So again, in number 2, I would divide by 760, but multiply by 101.3 so that I can get in kilopascals. In number 3, I divide by 1 atmosphere, but I would multiply by 760 millimeters of mercury. In number 4, I would divide by 1 again, atmosphere, but I would multiply by 101.3 to get 200 kilopascals. Notice I put a dot there so I would have appropriate number of sig figs. In 103 kilopascals, I would divide by 101.3 and times it by 1 atmosphere to get 1.02. And last, number 6, I would divide by 101.3 kilopascals and times it by 760 to get these numbers. And I tried to pay close attention to knowing what unit I have versus I want, and know if it's in proportion to what I had. So before, like in number 6, I'd weigh 10 times more kilopascals than I should have had. So again, I had 10 times more millimeters of mercury than I should have had. It should be proportional. Speaking of proportional, we should talk about how pressures and volumes of those gases are in an indirect relationship. So every time you increase the pressure on a substance by maybe adding more mass to the gas, the pace above the gas, it's going to push those particles together and they'll take up less volume. So in this simulation, every time I put the masses on, it makes the pressure go up here. Notice the temperature is staying the same. And then the size goes down every time I put more of the mass on. And so the graph kind of looks like this low curve. So question 1 we had to ask, how do we breathe? It's because actually what we're doing is moving the muscles around the diaphragm here. And every time we push the diaphragm up, it closes the amount of volume you have, which creates a high pressure, so the gas is forced out of your mouth. And whenever you move the diaphragm down, you're increasing the space in the lungs, and that makes it have a high volume, but then a low pressure, so gas goes back into your mouth to fill up that volume. So it's a Boyle's law. In Charles' law, the volume and temperature have a direct relationship. Every time I increase the temperature, you can see by the fire increasing it, and then you can see that this nozzle here, it increases the size of the gas. Notice this time I'm not changing the masses on top, so the pressure is staying the same. And the graph is going out from the 0 and in a direct relationship. So the question 2 we had was, why is Charles' law important for hot air ballooning? If you heat it up, the gases start to separate and they fill up the balloon, and then eventually the volume gets so high that its density decreases and the balloon can float. In order for the balloon to come back down, they have to turn off that furnace that was underneath the balloon. So the temperature goes down and the volume goes down, and it starts to deflate and go back down to the surface. And its density will be less because it will have less of a volume. More because it has less of a volume. Gay-Lussac's law is the last relationship you should know. You don't need to know these people's names, just know their relationships. So pressure and temperature have a direct relationship. And in question 3, when we were talking about the water bottle, it could actually be done in much bigger situations. In this case, a whole entire tanker had imploded instead of just the water bottle. So what happened was they had closed all the window, they had heat vacked it inside, cleaned the whole inside of this area with hot water, and then they closed the container. And what happened overnight is the temperature dropped, and whenever that happens, the particles get closer together when it's colder, and that makes the volume want to decrease. But in this case of the water bottle or this tanker, it can't decrease because the sides are rigid. So instead, it makes the pressure decrease, Gay-Lussac's law. And now all the gas outside wants to get inside to equalize the pressure, and it implodes from the outside in. We have another rule we talked about last year called Avogadro's law, that's saying that equal volumes of gases at the same time and pressure have the same number of molecules. So if you look at the picture on the left, argon, oxygen, and nitrogen have the same volume, the same amount moles, the same pressure, and therefore the same temperature. What's not the same is their masses, right? We know from the reference table their masses are slightly different. So what we're saying is the size of the atom doesn't matter, right? It doesn't matter what volume of the size or the radius of they're all infinitesimally small. And so their space between them is what's governing how much space they take up. The space between is governed by how much temperature and pressure you have. So here's another representation of that. They're all different sizes slightly, but it's not really about the size of the particles, but the space between them. And since they're all the same temperature and pressure, their space between them is the same, so therefore their volume is the same because the same number of particles are fitting inside those balloons if you count them up. So now we're going to combine them all together. Gay-Lussac, Boyle, Charles, and Avogadro to create the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. You don't only use this equation when discussing initial and final conditions of a gas, and if the factor is held constant, you can completely cross it out and eliminate it from the equation. The temperature has to be in Kelvin because Celsius temperatures can go negative or even 0, so in that case that would completely screw up all your calculations. Here's an example of the combined gas law. A bubble rises from the bottom of a lake at 8 degrees with a pressure of 6.4 atmospheres of water above it probably, and a volume of 2.1 milliliters, so maybe it's just like a little tiny bubble. We want to calculate the new volume of the bubble at STP. So we're going to plug all the first numbers in the first part of the equation. 6.4 was the first pressure, 2.1 was the first volume, and not 8 degrees, but 8 plus 273 for the Kelvin temperature on the bottom. We want to know what it would be at STP. Standard temperature is 273. And standard pressure for this atmospheres was one of the numbers you memorized. So at regular temperature outside, which is really frozen. That's why I'm showing a picture of a frozen lake. And 271 atmosphere, which is regular sea level, the lake. Well, how big would this bubble be? And the answer is 13 milliliters. So as it rises to the top of the surface, the bubbles get much bigger. So these bubbles that you're seeing in the picture were probably started off as really small 2 milliliter bubbles and became 13 milliliter bubbles as they rose to the surface. Here's another example. A gas evolved from the fermentation of glucose, and it has a volume of 0.78 liters and 20 degrees room temperature and 1 atmosphere, which is room standard level, sea level. What is the volume of that same gas if the temperature was a little warmer in the room and it was a little slightly higher than sea level? Would the bubble be bigger or smaller? So again, we're going to plug all the first numbers in on the left side. So it was 1 atmosphere, 0.78 liters, and then a Kelvin temperature on the bottom, and then change it to these new conditions of a warmer room and higher than sea level. And now what we see when we calculate by cross multiplication is that it becomes 0.69 liters, so the amount of gas that you're producing is much smaller. I probably assumed that it would be smaller if I thought about the fact that I increased the pressure, so therefore decreased the volume. But the problem is the temperature also increased. And when temperature increases, the volume should increase. So there are two different factors going on. And in order to figure out which one is presiding over this gas, I need to do this calculation of PVT so I can see which one's more involved. The last equation for today is PV/nRT, and this is the ideal gas law. It's used when only one gas is calculated and it is not changing its volume values. And then the units must be the same as these R values, which can be found on the reference table: liters, atmospheres per mole per Kelvin. So in this example, it says calculate the pressure of 1.82 moles of sulfur hexafluoride. This is the stuff that makes your voice not sound high like helium, but low. And when it's at 69.5 degrees Celsius and 5.43 liters. So this is the container it's found in, 5.43 liters. And this is the temperature, normal temperature in the room. So we're going to use a PV/nRT because it's one gas. The pressure is unknown, so I want to know how tightly, packed is this. The volume is 5.43 liters. The moles was given at 1.82. R is on the reference table. Temperature has to, again, be in Kelvin. When I multiply and then divide by 5.43, I find the pressure, in order to keep the gas in that container, is 9.42 atmospheres. Remember, normal pressure is only 1 atmosphere, so this is under high pressure. Here's another example. Calculate the temperature of 2.56 moles of a gas at 1200 milliliters and 680 millimeters of mercury. So again, we're just putting it in straight into PV/nRT, but you want to watch out. You want your pressure units to be the same as your R units. So if it's in atmospheres, we need to do that conversion first. 680 divided by 760. Then you can plus in the rest of your numbers. Remember, the temperature will come out in Kelvin. So 5.11 Kelvin, very, very cold in order to have that gas under those conditions. At this point, you should be able to explain the ideal gas law, convert between units of pressure, and use pressure, volume, temperature, or moles of an ideal gas calculated by PVT or PV/nRT.